Hello, I'm Alex Byer, and this is my ENME 605 Advanced Control teaching experience, where I will be discussing feedback linearization. Before I can explain how to use feedback linearization, I'd like to motivate my topic somewhat. As control engineers, we'd like to work with linear systems. They have lots of really nice characteristics that makes modeling and control approachable and easy. A nonlinear system, by contrast, has almost none of these properties. To that end, engineers and mathematicians have come up with sets of tools to build well-behaved linear approximations of nonlinear systems to make modeling and control more tractable. One of the most commonly used of these tools is the Jacobian, which we can use to build a good enough local approximation of a linear system that we can investigate behavior around a desired point, like an equilibrium. Above, I've shown how to use the Jacobian to linearize a system, which is one of the most common approaches. Once we've linearized our system, then we can begin to apply much more well understood methods of linear system control to it to achieve our desired performance. Some of the properties of our newly linearized system are: it responds to a small change in the input with a small change in the output, which is useful for control design. It also obeys superposition, which means that its inputs obey additivity and homogeneity. However, these linearizations only hold locally. The further we move from the point we linearized about, the larger the error grows. We can vary our approach a little bit to mitigate this issue, but ultimately we'll never be able to escape it within this method. In this talk, I'll explore the basic ideas of feedback linearization, a technique which allows us to not only develop much more robust linear representations of systems, but extends fairly naturally to a global linearization of a system owing to the way in which it's constructed. Our goal with feedback linearization is to come up with a specifically built coordinate transform capable of moving a nonlinear system into a set of coordinates in which it behaves like a linear one. We make our first assumption here, namely that the control law for the nonlinear system comes in two parts: a pure state feedback control, AX, and a design controller, BV. I'll be focusing here on the local CISO definition for the sake of clarity. Every argument I make here will be able to extend to the global MIMO case fairly naturally, via the addition of extra control inputs, which would turn that g of x times u term into a sum across all the control inputs, with the global applicability of the linearization hinging on the global truth of a few conditions I'll talk about in the next couple slides. However, before I can define the transform itself, I'll need to set up a couple of tools. The first tool we need is called relative system degree. We can find the relative degree of our system by repeatedly differentiating the output with respect to time until a non-zero term containing the output appears. The order of that derivative is then the system's degree. Notice here, though, that I haven't defined what this function psi is. That's because there's a slight problem with the definition. I've defined our output function to be h of x, where the time evolution of x is a function of our current state and input, with the input being a function of state. How do we then find the time derivative of a system like this? Luckily, that's where the second necessary tool comes in. The Lie derivative is a theoretical tool which helps to hold this approach together. First, we're going to use it to help differentiate our output, and eventually we'll use it to help construct our control law. So, to be precise here, we're going to view our control system as a mathematical construct called a vector field, which takes in one vector corresponding to an n-dimensional point, in this case the state and input, and assigns it to another vector, in this case either the output y or the time rate of change of state x dot. Our end goal then is to differentiate our output with respect to the states via the chain rule, right? So differentiating the output with respect to time is the same as differentiating the output with respect to the states times x dot. So we'll need to build a rigorous definition for what that means. Once we've accomplished this, all that's left to do is algebra. Similar to the Jacobian, the Lie derivative gives us tools to evaluate the rate of change of a multiple valued function with respect to multiple inputs. I'm opting to forego the full definition of a Lie derivative here because it hinges on Lie algebras, hence the name, to avoid delving too deeply into the abstract algebra. I'll have a source that goes through all of this linked at the end. In this case, the Lie derivative will look suspiciously like the Jacobian because I've limited myself to the special case of only using vector and scalar valued functions. These tools prove useful in many cases beyond the Jacobian because, unlike the Jacobian, they're fully coordinate invariant. You will never need to do a change of basis function once you have taken a Lie derivative. We can also extend our Lie derivative notation a little bit to enable us to say some really powerful things. For example, we can take mixed base Lie derivatives by repeatedly differentiating with respect to the state and multiplying by different functions. A function's 0th degree Lie derivative is just the function itself. Lie derivatives with respect to the same base, when multiplied together, will just add their orders together. So, all that said, let's get back to defining the idea of relative system degree and see how Lie derivatives play into this definition. First, we'll take the time derivative of our output, applying the chain rule as before to get y dot equals dh dx times x dot, where we then substitute in our known expression for x dot. Interestingly, all of a sudden our control input u has appeared. It looks like we found that our system order is always going to be 1 with this method. However, if we work this out and solve numerically, it'll reveal that for many systems, the LGH of x times u term is actually 0 for all state inputs. U seems to have appeared, but it actually hasn't yet. So to that end, we'll need to take repeated derivatives. Repeated differentiations of our output make use of the rules we defined 2 slides back. We see here mixed-base Lie derivatives and higher-order Lie derivatives appearing in the math. Each of these derivatives will follow the same structure laid out on the bottom of the slide. Our system degree is the smallest order n, for which the second term, the one containing the input u, is non-zero. Luckily, many common systems are of degree 2, making the LGLF matrix a square matrix very similar in construction to the Hessian. Ultimately, we want to get back to finding a coordinate system that makes our system behave linearly while still taking the same control input u. Luckily for us, we spent the past few slides building a particularly convenient set of coordinates, which not only give us a fairly nice set of coordinates to work in, but also help us find our control input u. This coordinate set is the output and its time derivatives. We'll take our coordinate basis to be those time derivatives of the output up to but not including the one in which our control input appears. Now our system looks like this. Our state vector consists of our outputs and its first n-1 time derivatives, for which we have expressions from the Lie derivatives we defined earlier, and conveniently they form an integrator cascade, where the zi plus 1th term is just the first time derivative of the zi-th term. From this integrator cascade, and our choice of not including the Lie derivative with the same order as a system degree, we find that the time derivative z ends up depending on u, the control input. We can use this to define a very convenient control input capable of canceling out all of the lower order Lie derivatives, leaving only v as our outer loop control input. It is also worth noting here that the choice of u is somewhat inherent to the method. Canceling the highest order Lie derivatives also cancels out a lot of the nonlinear behavior as well. This is why we included v in our control law earlier, to make sure that we still had a free parameter to control after this cancellation. I wrote this also assuming that LGLF would be a scalar to stay consistent with the presentation in literature. However, in practice, this will usually be a matrix and can be equivalently written as the inverse of LGLF times the rest of the control input. Now, let's take a step back and look at what we've accomplished so far. We've redefined our nonlinear system with control input u, which in turn depends on a desired control input v, to an integrator cascade in a different coordinate system whose control input v is the same desired control input from before. The way we've solved our integrator cascade naturally lends itself to being written as an LTI system, whose exact form we'll see in about 2 slides. Further, the steps we've taken so far allow us to have a lot of freedom in our choice of control law v. For now, let's just set v to be a proportional feedback law dependent on the transformed state z. Critically, we've managed to completely rephrase our system as an LTI system, which we know how to deal with. So now let's spend the remaining time looking at the strengths and weaknesses of this approach. First, a brief discussion of some of the strengths. So, while we have linearized the system, what have we really gained by doing this over the Jacobian? Well, the first is, we can fairly easily extend this to be globally true. All that we need to ensure is that 2 conditions are met. The first is that the transform needs to be differentiable, and have a differentiable inverse that exists at all points in the system domain, and that the derivative of the transform cannot have any discontinuities. If both of these conditions are true globally, then our linearization holds globally, which is something that is never true for the Jacobian. The final benefit of doing the transform this way, particularly when taken with our choice of v from 2 slides ago, is that we have the ability to set up our integrator cascade in a way that lets us place closed loop poles anywhere we'd like. This is an incredibly powerful ability that makes applying many of the concepts of linear control design quick, easy, and effective. Finally, I would like to spend a little bit of time discussing some of the drawbacks of this method, just to give a clearer picture. The way in which we built this transform is very, very robust and very useful, but is also likely to include unstable zero dynamics arising from any unobservable states. Additionally, because of one of our main underlying assumptions was the smoothness of both the source and target sets, discontinuities or otherwise non-differentiable dynamics are completely incompatible with this method. You just can't use them. And finally, and just speaking from experience here, while this method can theoretically work with a non-minimum phase system, because the requirement is that the inverse merely exist, not that it's causal and stable, it will perform very, very poorly if asked to control non-minimum phase dynamics, often causing singularities to appear in the math. Right, with that, I think I am a little bit over time, so thank you for listening. I've listed some of my sources on the slides, and any source which is freely available online is being hosted at the provided link, along with a copy of these slides and my speaker notes. Thank you so much for listening.